Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server Users Group Advanced DBA meeting. Had to remember what week of the month it is. Tonight, we've got a couple of announcements before the main event. So, first announcement is that there is a TriPass survey currently open. I'm going to paste it in chat for anybody who hasn't seen it yet. Please do fill it out if you have not. It helps us understand what we're going to do over the next couple of years and get a feel for what the user base would like to see in terms of presentation content and also general themes. So please check that out. It's about a 5-minute survey. Second, one of our user group members is looking to hire. Michael Moen is looking to hire somebody with an insurance background, ideally someone at the intermediate DBA level, and ideally also some analytics background. If you're looking for a job, that sounds like it might be a good fit. Hit me up via Meetup. Hit me up basically however you can. Meetup, Twitter, email, whatever. And I'll put you in touch with Michael. Third, Elaine Farstad has been a member of the group for a while. She went out to Tennessee a couple years back for a job and is looking to come back into the area. If there are any open warehousing or BI positions at wherever you work, or if you know of anybody who's got an opening, again, let me know. I'll pass that info on to Elaine. And with that, we are going to hand it over to Samir Behara, who will talk to us all about cloud native applications. So please take it away.
Thanks, Kevin. Well, good evening, everyone. This is Samir Behara, and today I will be talking about my experiences in building a data-intensive cloud-native application. Again, a little bit about me, Samir Behara, working as a senior architect with EBSCO. I'm a Microsoft MVP, Friends of Redgate. If you want to check out my blog, it is .netpipes.com. Again, a lot of this content which I will be covering in this session, I have already written detailed blog post around it. So you should be able to, if you want after the session to look at the slide deck or go deep into any of these topics, you can go to my site and get the details there. Let's see, moving on. So what are we going to cover today? So I would say this presentation will take almost around 40 to 45 minutes. And then in case there are questions, I will be open to answer them. But this is primarily a lot of sharing a lot of my experience with building cloud native application over the last couple of years, migrating a lot of the microservices, a lot of the monolithic services on-prem to the cloud using microservices, moving a lot of data stores, primarily handling relational, and then in the cloud, again, going using Polyglot architecture. So kind of I have tried to put this presentation in a way in which it will be easy to explain for me few of the architectural concepts and how step by step I took that journey and a few of the challenges which I faced. So I will try to cover most of these areas. So I'll start with monolith versus microservices, some of the design principles of microservices, how do you kind of deal with monolithic databases, look at few of the cloud migration strategy. There are a lot of there are different type of strategies which you can adopt based on your use case. We'll talk about polyglot persistence, different database, using different database for different use cases. What is horizontal, vertical scaling, a little bit about some of the architectural patterns which I have followed. Again, it's very helpful if you are going this approach towards a cloud migration strategy or cloud native event-driven architecture, circuit breaker, and I'll end up with talking a little bit about serverless database. So again, depending, irrespective of which cloud platform you are kind of using, either it's Azure or it's AWS or Google. So again, irrespective of that, I think these design principles, these good practices, I think fits in all. So I will try to basically not focus on any particular cloud platform, but just talk through a few of the concepts which will be applicable equally in irrespective of the platform. So starting with monolithic architecture. So this is how, when I started my career, a few of the applications which I dealt with were the monolithic services on-prem. So for the purpose of this presentation, I will be talking about an order management service. And we will see how we can break down this order management service into smaller components, and even how do we break down this monolithic database into maybe smaller data stores, right? So how does this monolithic architecture work? So you have a user, they are talking to this order management service. Maybe it's a legacy service having thousands of lines of code, and it talks to a monolithic database. So what can go wrong with this architecture? So basically, there are a lot of challenges over the period of time if you are working in this application, which you will be facing. Again, first one, code base, large code base, right? I'd say you have large amount of code here. How do you kind of, if you want to make a change in one class file, something else breaks. So a lot of interconnected, tightly coupled classes or components which you might be having inside this one legacy monolithic service. If you have a business requirement wherein you want to scale kind of your service, how do you scale your service, right? If you want to have like 5 instances of your services running, so that's kind of a big challenge with both the service and also the database. Longer development cycle. So if how do you plan your deployment? How frequently you're basically doing your deployments, right? So with such a big monolithic architecture or service, kind of you might be doing a deployment every 2 weeks, every 4 weeks, and there's a lot of testing which goes in to prep up for that deployment, right, before and after. So that's kind of one of the challenge with monolithic architecture as well. The deployments are complicated because you have to kind of coordinate with multiple teams, because there might be 5 teams who are working on this one application. So that's always a challenge. And then fixed technology stack. So this might be a .NET service or a Java service, and the data store. Primarily, I've seen a lot of legacy applications. Might be, say, relational data store, SQL Server. You might have Oracle, DB2. And then the next item, performance issues. If you bump into any performance issue, there are limitations as to how you resolve those performance issues, right? Because you have a lot of class files, a lot of components which are talking to this one monolithic database. So there's kind of a lot of troubleshooting, a lot of optimizations you have to do to improve the performance. And as I mentioned already, that tight coupling is one big challenge. You make a change to one class, something else kind of is impacted with the change. So kind of all these were few of the pain points which we faced while working with one of our key monolithic services. And I think the biggest one was the difficulty to scale the application. So when it comes when we want to go live with, say, another 500 customers next year, how do I kind of scale my application to cater to that load? So it was really difficult to do it with a monolithic service. So that's where the first step which you generally take when you want to break down your monolithic service is applying domain-driven design. So domain-driven design, basically what I've again, as I said, all these slides, I've just tried to keep it in pictures, trying to explain. So you have your business domain. Say first you try to look at, okay, the order management service. What are the different domains from a business perspective? So you start kind of creating the domains. So you say one is pricing, one is currency service, one is orders. So these are kind of my bounded context. And then you start creating your services. It's a little bit different method of thinking. Like generally, like earlier on in my career, when I used to get a new requirement, I used to first design the database tables. I used to go data first approach. But when you follow the domain-driven design, you're just talking, you're thinking through the business domains, and you are going kind of, I would say, the code first approach, looking at your domains, and then try to create your services which has its own separate data store. Again, the benefit which you get is obviously depending upon the use case which you want to suffice for your pricing service or currency service or order service, you can go with either relational or non-relational data store. So you will have the flexibility of going that approach. So once you start following the domain-driven design, you first take your first step. The next step will be like, hey, I have customers who are trying to talk to my microservices. So API gateway is kind of the front end of to your architecture, I would say, which you want to control the rate of request and also authentication. So all those are taken care at the API gateway level. So the request comes in, goes to the order service, title service, currency service, pricing service. All of them kind of have the same, they are sharing monolithic database. So what can go wrong with this architecture? It looks great, right? I would say, like from my experience, when we started breaking down a monolithic architecture into smaller components, I think from code perspective, things were easier. Create a title, a new service, the code, break down the old code into smaller components, easy. However, when it comes to the database, this was the challenging part. So kind of the first step was like, hey, let's have this shared database and let's see. But again, there are a lot of challenges which you will bump into if you follow this pattern and really, like, say, the amount of request which order service might be getting might be different than currency service. So the scaling will be different, right? So if you have the same shared database, basically you will have limited option in scaling. You vertically scale this instance just for order service, but currency service might not require the shared database to be kind of scaled because it receives less hits. Say you have 4 teams, different teams working on each of these services. If the team makes any breaking schema changes on order service and deploy it, they might break title service, right? So there's a lot of coordination required as well as you're working through a shared database. Scaling is one challenge. Making schema changes is another challenge. Just maintenance, coordination. I would say those will be the primarily um, uh, concerns which you will have while working in such a solution. If you have a performance issue, how do you troubleshoot, right? One solution cannot fit in all these four services. So kind of something to look at. So we saw these challenges, and this led us to, okay, we need to start breaking down this monolithic shared database. And this is the most difficult part, I would say, in your journey from monolith to microservices. So one key principle which I would like to focus here is when you're talking about database, say you have two services, you have order service, you have pricing service. So always need to keep in mind that, hey, the order service has its own data store. It can modify this data store. It can read write into this database, but you should not allow the order service to modify data which is in the pricing data store. That's kind of an anti-pattern, so we need to stop it. Earlier we did not control it, but after like few months we saw the issues, because you need, for the pricing database, you need the pricing service kind of to own that data store. Any changes has to go via pricing, right? If order service needs any data from the pricing database, it has to make a call, API call to the pricing service, and let pricing service fetch the details from this pricing database and give it back. So this is one key principle, I would say, which you need to follow when you are in this journey. So this is kind of the ideal microservices architectural diagram, I would say. You have users talking to some UIs, which are calling behind the scene order service, title service, currency, and then they have their own independent data store. So this is the ideal state. Again, it takes time to take this journey. I've just showed the initial state, and this is kind of the ideal final stage. But this architecture has a lot of benefits, I would say, like starting with, hey, if I want to make a change to just one component, I can just go ahead and change something in the order service and deploy it. I don't have to actually, if it was a legacy application, which we saw, um, I would have to kind of deploy the entire application, right, to make that change, to make that small change into order service. So that's kind of the biggest benefit. You have a shorter development cycle, deployments are faster. If you want to scale now, the scenario which I explained earlier, wherein order service has a higher scalability requirement than currency service. So in this case, I can have a different scaling defined for my order service. Right technology stack, depending upon my use case, I can actually go with any of the data stores. I don't need to stick with a relational. I can go as a NoSQL. I can go to use any time series database if that's kind of what the business requirement is. Business domain driven. So domain driven is good because when you're talking to your business stakeholders, basically you're talking in terms of these domains, right? So you talk in terms of order, title, currency, pricing. So you are able to basically get the requirement from the business and translate that into your service logic. Resiliency, observability, high cohesion, loose coupling. So all these are like a lot of the advantages which comes with microservices. Again, there are a lot of challenges with microservices as well, but kind of I would say the advantages are far more um, um, relevant compared to the drawbacks. So the journey again, starting with monolithic database. You go to service-oriented architecture, then go to a microservices architecture. So here we start with a monolithic legacy application, talking to a single database. then you have a shared database, and then finally you kind of have an independent databases for each of your services. Again, you can go from step 1 to step 3 as well. There were scenarios where we did that, few use cases, few applications where we went directly from step 1 to 3. And in some other cases, we were as we were developing, we went from step 1 to 2, then 2 to 3. So one critical aspect which I mentioned was faster deployment, right? Once you have once you're breaking down your monolith into microservices, you have 4 different services. So you need to have an automated pipeline built in to actually get the benefit of your microservices stack. So that's where I think this is basically a very generic pipeline which I've tried to show here. So a user committing code into GitHub triggers a build, and you can use any of the CI tooling, Jenkins, Azure DevOps, as your kind of tooling. And then you can have different stages defined in your pipeline. So you can have a testing stage, which is very critical, right? You deploy, you commit something to your feature branch, you run all these stages. You run a testing stage wherein you run all your unit test. Again, not just limited to your code, to your application code, but also to your database code. Like you can write T-SQL a unit test covering your stored proc logics. Similarly, quality. So if you want, you can use SonarQube. This is something which has worked great for few of the use cases which I have in past. Basically does a static code analysis. It has a set of rules for each languages. Like if you are C#, SQL, Java, Python. So it has a fixed set of good rules which you should follow, and basically it runs all those rules against your entire code, and it will identify okay, what are the areas where you are not basically following the good practices. So kind of a good way to make sure your code is of topmost quality. Deployment, you can use Docker containers for automating your deployment. Load testing, use any of the tools like JMeter, load runner, kind of to do some load test or performance test. Security, if you want, you can integrate Zap, is one of the very popular libraries to integrate for security testing. So overall, um, you need to have a automated CI/CD pipeline for deploying your microservices, or else you'll not get that benefit wherein, hey, you won't be able to deploy it on a smaller cadence as business needs. So cloud native architecture, again, what um, what is cloud native architecture? There has been a lot of questions. Generally, even when I do this presentation, I get this question. So I kind of try to put this diagram just to say that, hey, this is kind of following a combination of all these patterns. Like, yeah, you are doing DevOps, you're deploying using containers, you are kind of following all the microservices principles, you have a CI/CD process. So kind of a combination of all these good practices is what you will say when you're thinking about cloud native architectures. So coming to cloud migration strategy. So this is interesting. Depending upon your use case, you might have a different cloud migration strategy. No migration strategy will be the same. I would say like my use case will be different than what yours is. But depending upon what the goal is, right? Why do you want to move to the cloud? Um, what are the business requirements? Are there any deadlines? What are the issues which you are currently facing on-prem? Why do you want to break down your monolith and go into a microservices architecture? So kind of first you need to look at, consolidate all your problem statement, right? And then try to figure out that, hey, does it make sense to start moving to the cloud, or in a lot of cases, even if you re-architect a few of the components, monolithic components on-prem, that might fix your issues. So again, um, use cases, based on the use cases, you can go either approach. But I would say, like, from a top level, looking at it, you can either do a migration strategy, I would say, like just a lift and shift. You're lifting your on-prem application, moving to the cloud. And when you do that, again, it's not always just lift it, shift, and put it there. It will require some code changes, but again, minimal code changes. And when you do that, when you do it, that lift and shift, if you have a legacy application which is say 15 years old, written in a older version of .NET, a lot of legacy bad practices which you have been following, you will not get the real benefit when you actually lift and shift. So basically, that will be kind of your first step. After that, you will need to kind of start optimizing your monolithic service to take the real benefit from a cloud platform. And again, we have seen that it's expensive on the long run. Again, it's debatable depending upon your use case, how much time you have to do to kind of complete this assignment, I would say. How big is your service? What's the business requirement? So all of these plays a role here. The second stage is modernize. Obviously, you say, okay, all this legacy code, we cannot refactor this. So maybe let's start fresh. Let's start creating the microservices architecture. Let's break it down. Let's start creating those small components, use containers, and let's build it from scratch. So again, might take time, right? Depending upon your legacy application, how big that is. But if you do that, you will see you will be building a solution which is kind of where you can leverage the true benefits of cloud native, I would say. But again, this is very time consuming. It's a cost optimized solution, but since you are talking about actually refactoring your entire application, it might take some time. So talking about 6 hours of cloud migration here. So I've tried to put in like on the couple of axes, cost and effort, and the time to migrate. So there are 6 hours. Retire. You look at your one of your on-prem application and say, hey, we don't need to kind of move it to the cloud. I think this is an application which has not been used. So just let's retire it. Easy, right? Retain. Again, look at an application. Yeah, we need this. Even though it is like 10 years old, we need this. Rehost, kind of try to move it. You're trying to move it to another platform. Replatform is where you're moving, again, doing a lift and shift, and you're using some of the managed services which the platform provides. Repurchase is, okay, I'll use a SaaS product, a third party, and to build, to just take the functionality into the platform and just use it. And refactor is what I said. Okay, you start from scratch, you refactor your application and build it. Again, takes time, cost and effort as well is higher, but there are benefits of doing that as well. Polyglot persistence, again, one of the key benefits which we saw was going polyglot. Basically, when we had a lot of these microservices, we started breaking down into multiple components. We got the flexibility now to think about, okay, what data store makes sense for that particular component, right? So we had the flexibility to just not use relational for all the use cases. Again, if we had a use case wherein a NoSQL solution would make sense, yeah, let's go ahead. So kind of few of the data stores which I have worked in, like relational, again, like time series database, something like I would say Prometheus is very popular in the Kubernetes space, wherein you store those time series data and kind of query Prometheus using PromQL. You can use DocumentDB, wherein there is no structure, if no fixed schema which you need to adhere to. You can create kind of if you want to add more columns and all, right, you can add another 10 more columns to a particular document and then query it. So there are a lot of use cases of a document database. Key value is where kind of performance, if you improve performance, you have a key value stored in the database, fetch it, better performance. Graph database, when you are dealing with, I would say, a lot of interconnected data sets, that's where graph comes in. Search database, something like if you have some use cases, business use cases, wherein you want to do searching, like a look at an e-commerce site such as Amazon or something, you might have some use cases wherein for Elasticsearch kind of data store, wherein you want to have some faceting in your UI. You need to fetch records, have different more search requirements. You can go with something like Elasticsearch. And you have in-memory database, something like Redis, which is very popular. Like instead of calling the database all the time, okay, let me store the data in memory so that I can get an optimal performance. So it's all about selecting the right database technology for your particular workload, depending upon, as I said, a lot of scenarios. Is your database, like, is your workload read heavy? What is kind of the latency or the performance latency, which performance expectation which business has from that particular service? Um, so all these plays a role into what kind of database technology you go with. So once you're in a microservices architecture, I think you have that flexibility to select the proper data store for your own use case. And I would say that that has worked really great for at least for a lot of the services which I have built in past. Um, we try to go with the requirements first, see, okay, what is kind of the workload, what are the expectation, is it a write heavy workload, read heavy, so all those plays a role into kind of selecting um, the right technology for your workloads. So again, I've listed down a lot of these popular databases: MongoDB, Cassandra, Redis, SQLite, Prometheus. Again, you will have the flexibility to choose the data store you want to. So coming back again to just talk about the database scaling, which is really important as you um, are trying to say you have a use case where in beginning of every month you get a lot of calls to your service. At that point, you need to scale your application side as well as the database needs to scale to kind of be able to cope up um, with that load. So what are the options you have? Vertical scaling, again, you can increase your database size, right? CPU memory, you can go with a bigger instance. And then horizontal scaling as well, which is really important, I would say, when you're in a kind of a cloud native architecture, you would like to scale horizontally. You can say, instead of having two instances, if there is, say, you get a heavy load, you can create another read replica and then just basically have a load balancer and then route the request from the application against three instances instead of two. So kind of horizontal scaling is where you have a newer instance to cater to the load, and when the request count reduces, you basically auto scale it back. So I'm trying to, in this diagram, I would say I'm just trying to show how the read-heavy workloads work. Say you have increased users load coming in. So you have a load balancer in place. Your application starts auto-scaling as your request, as the number of calls to your application stack increases. You go from one instance to say maybe 5. You have your primary database instance, but again, that might not be able to handle all the read load. So in those cases, what you do is you create more read replicas here, and then let your application instances read from those read replicas. So kind of this is a very ideal way to how you handle read-heavy workloads in the cloud. Again, works great. So the next one, which I have, is multi-AZ deployments for high availability. So in cloud, you will have something called as availability zones, I would say, just to make sure that, okay, if one of the data centers is down, you still have a backup, right? You need to have a high availability. So in those cases, I just wanted to show that, okay, you can have a standby instance in a separate data center, which you can spin up if your primary instance goes down, your applications can immediately start reading from the replica instance. So same thing, multi-AZ deployment for read replicas. Here, you have different data centers. You have the master instance. Again, if you have a read-heavy workload, what you do is start creating more read replicas. And basically, you can have a load balanced endpoint for your database, and then all the requests will be kind of sent to these read replicas. And that's how for read-heavy workloads, I think you can scale in and scale out based on the traffic which you are receiving. So the next point which I wanted to touch base is database sharding. And sometimes when is sharding important? Basically, it's not just about reads, I would say. Sometimes if you want to optimize your writes, this way you can start having smaller shards, right? You can have a number of nodes here. So what I've tried to show here is, say you have a customer database, and you are basically trying to optimize the write performance. So this is basically, I would say, partitioning. So you are saying, okay, any customer starting from A to D gets stored here, E to J stored here. So kind of you have a number of nodes, and you are basically writing to these small instances, and that's how you get a lot of these optimization from a write standpoint. But there is a big challenge here, right? If you kind of shard it in this way, you will end up having some imbalance in your shards, right? Because say there are a lot of customers starting from A to D, or O to S, and then you will have a less number of customers starting from T to Z. So you don't want to have these imbalance. So you need to balance your shard for optimal performance. So that's where what you do is you have a hash strategy. Basically, you create a hash algorithm so that you can kind of distribute the load in a proper way between your shards or nodes. So kind of having a sharding strategy helps there. So another key principle as you are trying to improve your database performance is caching. A lot of, if you're working on microservices architecture, you don't want to kind of make repetitive database calls, right? When you start looking at the performance, generally you will see that, okay, I'm making a database call that's kind of slowing me down. So what's the way in which, if I get repeated calls, how do I not make that database call? So basically you introduce a caching layer between your service and your data store. So first you check whether, hey, is the data in cache? If it is there, yeah, read from the cache and return it. If it is not there, you go to the database, fetch it, save it in the cache, and then return it. Again, it's like if you're basically, there are some frequently accessed data, so you can store it in the memory, and it's always faster. And then you are also reducing the load on your primary database, so that's always works well. You can define kind of a cache invalidation strategy. Okay, how long time to live value as well, like how long you want those records to be stored in the cache, and after that you will invalidate those. So in this diagram, I just wanted to show there are a lot of databases here, as you see. There are a lot of services. So say a request comes in, it basically traverses through multiple services, goes to the database and fetches all the information, right? So say one of your database is down. So what happens? That entire communication channel is down, basically, right? Because you're kind of dependent on that database. What happens when this database is down now? So you'll have a lot of channels, communication channels, which will fail now. So that's where you want to protect your application. If you have a database failure, if your database is down, you don't want to your services to kind of be in a degraded state. So how do you handle this scenario, right? So kind of a very popular design pattern is circuit breaker. And this is used to kind of design some fault tolerant microservices. What we do is we create a fallback method. If your service is down, basically you can say that, okay, give create a fallback implementation, right? Say you can return, say, a particular fixed value, or you can return an error message or a generic message back to the customer instead of like saying, throwing out a bad error message. Or even in some cases, if your database is down, if you are using queues, what you can do is you can keep storing those messages in the queues. And once your database is up, you can start processing them. So circuit breaker pattern is really helpful. It helps you to kind of design your application and make it more fault tolerant. If there are failures, handle it gracefully. We don't want to actually have cascading failures in our microservices architecture. So basically, let the service which is interacting with this database send a graceful message back to the consumer. And once the database is back up, it can start resume the processing. We don't want a single point of failure, right? So what I'm saying about queues here, again, event-driven architecture is a good practice to follow. Like if your order service is calling pricing service, is calling currency service, there is kind of a tight coupling which you are building in between the different components in your architecture, which you should kind of try to avoid that. So there's where you can introduce queues and have some loose coupling, right? So order service, a request comes in, puts order service just puts a message in the queue and gets starts getting responsive to cater to the next request. Pricing service is subscribed to this queue, picks it up, processes it, picks it, puts it in the pricing queue. Currency service picks it up. So kind of this is loose coupling. Even if your pricing service is down here, you basically keep storing all the messages in the queue. And once the service is up, it will pick the messages and process it. So kind of it gives you a lot of cushion in case of failures. So it's a very good practice to have kind of a loose coupling between your components in your services. Designing for scalability, that's what I think has been one of the key focus as to why to build this new generation services in the cloud. Like if you have your web server talking to an order service, talking to a database. Again, if your application gets like millions of requests, say in beginning of every month, or say in a holiday season, if you have a e-commerce application, what do you do? Basically, you put those messages request in a queue, and then you scale your order service. Instead of having one instance, you run 5 instances, 10 instances, and they start processing, picking up the messages in the queue, and processing them. So kind of you need to design your application so that they scale in and scale out based on the load. So coming back here to talking a little bit about serverless architecture. So we talked about monolithic on-prem application, we have VMs, then we are deploying it using Docker containers. So you have public cloud, private cloud. However, I think serverless has been very popular of late, wherein, again, it doesn't mean that there are no servers. It's just that you don't have to manage your servers. Someone else, like a particular cloud, a third-party cloud vendor, they manage your servers, and you just kind of deploy your application, and you don't have to deal with kind of managing their underlying infrastructure. And that's all to serverless here. So serverless databases, again, are, I think, they have a lot of good use cases when you are kind of trying to build services in the cloud platform, I would say. Try to look at the serverless offering. So again, it helps. There are a lot of use cases, as I said. Say you don't want to over provision or under provision your databases, right? And the on-prem side, I've seen a lot of databases which are kind of under provisioned. A lot of them are over provisioned, and we try to add more disk to it. So you don't want to land up in that state in the cloud. You don't want to pay for unnecessary for resources which you are not using. So in those cases, serverless makes really good sense. Like if you have an increased load, kind of you can scale your database. If when the load decreases, you scale back in. So basically, you're not paying for unused resources, and you're scaling back in, scaling back out, and basically making good use of your compute resources. And all these is automatically done. The scaling in, out is taken care by the cloud platform. So some of the use cases which I've from my experience I've seen makes really good sense when we are talking about serverless is like when you are creating some test databases. Say your development teams, they are doing a brand new development, and you don't know what the workload type is, right? So basically for those test databases, say you are working 8 to 4, and then you go out, come back next day 8 to 4. So basically for those instances, you can have a serverless database, it gets spin up at 8. Once you start complete your work, it will get scaled down, and again next day when you come in, you start calling your database, it will just scale back up. So something test databases makes good sense. Variable workloads, if you don't know, if you're creating a new project and you don't know exactly what kind of workload you're expecting, so I would say, like, let's go with serverless and see and just get a feel of how your services, how many requests you are getting, how your database is scaling in and out. So you'll get an idea as to what's the correct size of the database which you will need to configure. If you have a new database development, again, you can go with serverless to start with in a test environment, makes more sense. Infrequently used databases, say in your so say if you have an application deployed in production, you might be having different environments, right? You might be having a live environment, you might be having a say an integration environment, a dev environment, a testing environment, maybe a staging environment, right? So once you create a service and deploy it and it is live, the production environment, it's being used. The integration environment, yeah, maybe it's getting used, but what about the staging environment? What about the dev environment? If you're not using those on a daily basis, you might not, because if there are no changes happening to your service, you might not be actually going into that service code. So it makes more sense to have some serverless databases there. Again, a really good cost-effective solution in the cloud, because you're not guessing what's my requirement. You know that your database will kind of adjust its capacity based on the load which is receiving. And if you have some unpredictable workloads, it makes really good sense to go this approach. So this diagram, I just wanted to show how the database, the serverless database, is kind of working. So if you look at, this is a period of 2 weeks. So you see the spikes. Basically, this is kind of the number of the capacity units of which I have configured for the serverless instance. So for a particular period, it will go to 2 capacity unit. When there is no use, it will just scale back down to 0. Again, there is someone calling the database, it will spin up and again cater to that request. So again, it's all these spikes. So basically, for all these periods where you see 0, you're not basically paying for any database, the compute resource, you're not paying it. The only catch is it takes a little bit time, and it has a warm-up period. Like if the database is scaled back down, the first call which you make generally takes a couple of seconds, and but after that, you will not even know. Again, we use serverless for a lot of applications in production as well, so it works seamlessly. Again, I think that's all I had for the content. I had some questions, previous questions, but I don't know how I do it here. Yeah, so thank you, everyone. Again, if there are any questions, you can always reach out to me at Samir Behara in Twitter. Kevin, is there any places, or is there any conversation which happens here, or how do we take in questions if there are any?
Yeah, so if there are any questions from chat, what we'll do is I'll relay them to you.
Okay.
Andrew says that the talk was great. I actually do have a question of my own.
Sure, go ahead.
That is, suppose that you end up landing in SQL Server as your microservice database of choice. With an architecture where each microservice gets its own database, how do we handle referential integrity between services?
Yeah, that's one of the challenges which we have seen as well. Again, our use case was where we had a lot of this polyglot. Based on our requirement, we went with a lot of Mongo, Elasticsearch, Redis, different databases. But yeah, again, like say, when you have, we have SQL Server in the cloud as well. And there are a lot of services where we decided that, hey, let it be monolithic, and we start because like for this order management service, we had title, we had pricing, and it was so much interconnected. We were actually not able to break it down properly. And when we did break it down, we had a lot of duplicate code shared, and it was really difficult. So we had a shared database between those components. That was one use case where we really struggled to break it down. And then there was one more project wherein we have multiple SQL Server instances between these services. But again, there is not much overlap. I would say those domains were so independent. We did not bump into that referential integrity issues. So again, depending upon the use case, I think we got We had a challenge wherein we went with a shared database and some other use cases where we just kept it separate. And it worked for us actually because of the domain which the business had in for those cases. Those issues, Kevin?
I have run into those issues before, and a lot of it comes down to I'm not really sure what to do here. I can try to have central services that are referentially integral within each other, within themselves, and deal with it as best as I can otherwise. But you run into the issue that I don't really trust the app to get it right when I have database constraints, because I've seen too many cases where the app just doesn't quite get everything right.
Absolutely. And again, this is very interesting because one of the projects we had in as well, which I worked in the past, had a similar requirement. It was a big monolithic application SQL server in on-prem, and we wanted to take it to the cloud. And what we had to do actually was kind of create another instance in the cloud, like as the first step, replicate the data from on-prem to the cloud, create all the new microservices in the cloud, and which all started reading from that replicon in the cloud, replicon SQL server in the cloud. It was a shared instance, but kind of that was the first stage. And then we started shutting down few of the legacy components and then move everything after a couple of years to the cloud. But yeah, there are a lot of challenges when you start breaking down the monolithic database. So it's always a tough use case to solve.
Yeah, it makes sense. Looks like there are no other questions from chat tonight. Got some people saying thank you so much, and I will reiterate that. Thank you so much for presenting tonight. It was a very interesting presentation, a very interesting topic, and I learned a lot from it. So thank you.
Thank you again. It was a pleasure, and thank you all. Again, as I said, in case there are questions afterwards, I would be happy to answer them offline.
All right, wonderful. So this wraps up tonight's Triangle Area SQL Server User Group meeting. Next week, we're going to have Jess Schultz talking to us about migrating from database backups to backpack files so you can load them in Azure SQL Database. So come check that out, and we'll see you again soon.